last action is that in the last lecture is that we reformulated at the very end the scattering equations as the residues of a quadratic differential p squared, where p was just the sum over ki over sigma minus sigma I. And the second thing that we concluded was that our tentative action that we want to construct should take the form S is SA, where I've now put this A for what I've called bare before, plus some meta part. And as I said, we're going to focus first on this SA. Now, especially if you have some, let me maybe also remind you. So our goal here is we want to construct a Voltrami theory that reproduces the CHY scattering amplitudes for us. Because if it doesn't reproduce these, then we want to use this to extend these to loops. So it better reproduces these. Okay, so the first thing is that if you have any familiarity with string theory, then one natural thing that we know SA has to do, it has to be a theory of maps from that map X, say from sigma, to Minkowski space. And I'll be general and keep this in d dimensions. Yeah, apologies. Something that I should have mentioned really is that the CHY representation, I've written it explicitly without any dependence on the dimension d that I'm in, with some assumption that d is larger or equal than 4. And that is really true. It holds in any dimension d larger or equal than 4. So this is something that for now we're just going to keep in our ansatz here. And so this is what we wanted to do, and we wanted to put p square equals 0. And we know because the whole construction of the CHY amplitude has such a chiral look to it, it's probably a good idea to make something that looks relatively chiral. So with all of this, let's look at a first attempt. Just putting together what I've just said suggests that our action SA should have the following form, where my tilde really just means this is our first attempt right now. Standard factors, and then we want a kinematic term, and I've just put a chiral one here for precisely that reason that we just said, and because it's the only thing I can construct where P remains a chiral one form. And then we said we wanted to impose the constraint P square 0, and so I will do this just with a Lagrange multiplier here. Okay, so just staring at this, what I've written is just what you would hopefully naturally write. It's a first order action. It is chiral in the sense that the fields that we're really interested in, P and X, are only chiral. I've imposed the constraint P square equals 0, as I've said, with a Lagrange multiplier. But something that is really important and that deserves to be highlighted is that we have no alpha prime in here. There is also not even a scope for including alpha prime, just by mass counting. So this stands a chance. This has a chance at describing field theory. This is good. This is what we were hoping for. Now, to promote this to a CFT, at this point it isn't. To promote this for a CFT, we have to assign conformal weight to all of our fields. And maybe just let me remind you, for those of you for whom the CFT course is maybe a bit further back, that remember in a 2D CFT, conformal transformations are just the same as analytic. And so what we mean by a primary field, let me just put this here as an aside. Our what we mean by a primary field, phi of h and h bar, is that it transforms under conformal transformations, meaning analytic coordinate transformations, as follows: phi prime of z prime z bar prime is dz prime dz to the minus h dz bar prime dz bar to the minus h, and this is now just my phi fz and z bar. Okay, so in other words, in 2D, we know that we can associate the conformal weight with the form degree. So in particular, this is important enough to spell out. So in particular, for h larger than 0 in my definition of the primary field here, we often say that it's an element of omega naught of sigma and k, where k here is the canonical bundle, sorry, to the h here, meaning really that this looks like dz if h is 1. And for h smaller than 0, the opposite is true. It just transforms in the tangent bundle also to the power h here. Sorry, I've implicitly restricted here to the holomorphic part because that is going to be the one that we're most interested in. Okay, so to promote this to a CFT, then we have to assign conformal weight. And we've already concluded that for P, I'm going to write this now as the full h tilde in 1. HP should be a 1 form. H mu, let me be detailed. X mu, we said we wanted to have just as maps. So this should just be 0, 0. And for E tilde, you can just check that this is now just determined by the action. Just check what balances the weight of the P square here. And this is 1 minus 1. Now, I should mention maybe that E tilde is often, if you know this from string theory, called a Voltrami differential. So if you've seen this before, if not, this really just means that E tilde will look like z bar z, dz bar over dz. Okay. Then now we have a CFT on our hands, but really we don't have a worldsheet theory yet. So to promote this to a full worldsheet theory, what we should be doing is we should also gauge the chiral, well, the stress energy tensor, but because everything is chiral, we're just going to gauge the chiral part. Which you can check, and which you should check, is just P dot dx. Now, something that is good to check and potentially also in the homework, depending on which part you do, is both that this is actually the correct chiral stress energy tensor, and the other bit that is good to check is that this actually gives the fields the weight as I've defined them, the conformal weight. So for that, just recall that for any primary field phi, the relation between T and the OP between T and the field phi involves the conformal weight here. So this is something that I recommend you go and check that this works. Now, finally, let me just conclude by actually writing out what this gives us. So if we do all of this, then we arrive at the following bare action before. And I'm just writing currently the first terms in the action that we had before. So this is nothing new yet. And we concluded that we should also gauge the chiral stress energy tensor, which I've done here with just a field that is conventionally called E. And now you also see why I put the tilde on the other E. Let me just mention that E has the same weights as E tilde. And this is where you would have probably seen actually the Voltrami differential from string theory. Now, this is our important first result. This is what is known as, well, this is our bare action, and it's known as the ambitwister string, in this case, just the bosonic action. Okay, so we'll spend the next few minutes looking at this action in some more detail and seeing what it tells us before we go any further. So I've pinned it up here again to help you remind you what it is. And the first thing to notice is that there's a couple of symmetries, and that's entirely unsurprising. We know this because we gauged a couple of curves. So in particular, the last thing we did is we gauged the chiral stress energy tensor. So we better find chiral worldsheet diffeomorphisms. And indeed, I've given you here the transformations, and these match the standard transformations that you might have seen for an arbitrary primary field. Now, this is unsurprising, and this is good because this tells us that we really do have a worldsheet theory on our hands. However, there's an additional set of symmetries, which comes from having gauged the p-square constraint. Now, if you want, we can call them the ambitwister ones. And they're the ones that are generated by p-square. And if we look at them in detail, we can see that what they tell us is that we can translate x by p. So in other words, we translate along null geodesics, and then the rest just follows through. You can check this explicitly in the action. So what we've seen is that this generates translations along null geodesics. And in particular, this suggests to us that what our target space for the theory actually is this space of null. I should say this is a complex space. Everything we're doing is complexified. Now, this target space turns out to be called PA, where A is known as ambitwister space, and PA is just the projective version thereof. So PA is just A mod P by dP. Okay, so I've spelled this out here in a bit more detail. So ambitwister space is a set of Px in the cotangent bundle T star M, where P square is 0, and we've gauged translation along null lines as well, identified X with X mod P. Now, there's a few points about this space that I would like to make. So the first thing is, maybe just for general aspects, the dimension of A, you can just count from what I've said above, is just 2d minus 2. And for PA, because we've gauged the scale, this is then just 2d minus 3. And there's a nice correspondence, but it's not an entirely local correspondence. So you can see that I've drawn here a cartoon of 2 points, x and x prime, and a null ray L. What this looks like in ambitwistor space is that we'll have a quadric in projective ambitwistor space, a d minus 2-dimensional quadric, which I've noted by x and x prime, which you can think of as the full null cone for the points x and x prime. And where they intersect in precisely the light ray L, which is a point in ambitwistor space, but which is a full light ray, obviously, in standard Minkowski space. Now, 2 more things that I did want to say is that this gives us an intuition, that, or at least that this meshes up with our intuition for massless field theories. Obviously, this space is a good space to describe massless field theories because it seems to know very naturally about how they propagate in space-time. Now, the other thing that needs to be said is about the name ambitwistor space. We won't touch upon this, but this has really historic origins. And in 4 dimensions, it does make sense. When you restrict to 4 dimensions, ambitwistor space has a very nice representation as a quadric inside of twistor space and dual twistor space. If that means something to you, great. If that doesn't mean anything to you, that's also fine. We won't be needing it, but you will have the chance to explore this on the homework if you choose to do so. Also, leading on from this, there is a very rich geometry underlying this, and ambitwistor space itself is a symplectic manifold. Projective ambitwistor space is a contact manifold, and if you're interested in that, I will post some references where you can learn more about it. What we'll do here is we won't talk about that, but instead we'll take just a CFT approach and just see what comes out of our model. Now, last but not least, I said our target space is actually the projective ambitwistor space, with PA is A quotiented by P dot dp. How do you see this? Now, the best way to see this is actually, if you remember that our P in the action was a 1 form. So just because of, if you look at how it transforms under conformal transformations, this means that it picks up a scale. So it's only defined up to a scale because we quotient by those transformations. So that means that our P here, since it only is defined up to scale, we should quotient by that in our target space, which reduces us from just ambitwistor space to the projective ambitwistor space. Okay. At this point, we've said everything that we need to know about the classical action. So we've looked at the symmetries in detail. I've spelled them out for you. We know that the target space is the space of the complexified space of non-geodesics. So that gives us a good intuition for why it should appear in something that will describe scattering of massless particles. The one thing we want to do now with this is quantize and calculate an amplitude. However, before we just dive into this, let me give you a brief intermission. This is hopefully just a review of things you heard either from Ollie or previously in a CFT or string theory course. And this is just going to be some basics about chiral beta gamma systems. And I won't distinguish in my notation. I will call everything BC. So we will use this obviously everywhere. And whenever I don't write something in great detail, that is probably because I'm just using something standard from this slide. So in case of doubt, just go back to this or ask me. Now, what do I mean by this, by the chiral beta gamma system? This is what you would have seen in string theory as a CFT of ghosts. So we would just want to consider the action S is 1 over 2 pi integral over B d bar C. And I want to not specify what the conformal weight is. I will just call this lambda for B. And that immediately implies that C, just to match this, has to have weight 1 minus lambda 0. And let me also say that I'll use epsilon. Epsilon is -1 for fermions and 1 for bosons. I've seen literature use this also the other way around, just so that you know my conventions here. So in particular, I will use B and C variables for both bosonic and fermionic systems on this slide only. Now, the first thing that you can find from this is the OPE. So this is just a free system, and you can see that, well, C of Z, B of W is just 1 over Z minus W, which implies, of course, that if you swap this around and you have B of Z, C of W, that you should find a minus 1 over Z minus W, mainly just W minus Z if these are bosons, but if they're fermions, you pick up an additional sign from commuting them. Now, we also have the stress energy tensor, TBC, that we will use frequently. And so let me just give it to you in general. This is minus lambda B dc plus 1 minus lambda dBc with central charge anomaly. I should say, so all of these are standard calculations, and you'll have a choice in the homework between two problems, and one of them asks you to verify these. You just find 2 epsilon 6 lambda square minus 6 lambda plus 1. So let me just remind you, you calculate the central charge as usual just by looking at the OPE between two of these stress energy tensors. Now, there's one final thing that I want to mention, and that is something that is often useful, is the number of zero modes. And this is just, I'll give you as n, sorry, looking at my own conventions, nc minus nb, which is 1/2 times 2 lambda minus 1 times chi, where chi is just the usual 2, 1 minus g. Okay, let me just point out this one, there's various ways you could prove this. In CFT, this is something that you would sort of look at by sort of background charge conservation. But if you're more coming from a more mathematical perspective, this is something you would have seen as the Riemann-Roch theorem. So this is also from the Riemann-Roch theorem, something that you could derive just very quickly, obviously assuming this theorem. Okay, so that's all my intermission. If I state something as easy to calculate or something, it probably means that it just relies on what I've put on this slide here. Now, end of intermission, we're going back to our ambitwistor string action. And what we would like to do now is to do a Brst quantization. Now, I'll be schematic with this, just in view of time. But feel free to ask me questions if there's something you don't understand. Now, remember, we're gauging two currents here. We're gauging T, which I remind you is minus P dx, and we're gauging, well, 1/2 P square here. So we'll proceed as usual, and we'll introduce ghost systems for these. And so we'll introduce one ghost system that I'm going to call B and C for T, and one ghost system B tilde and C tilde for H. But remember, everything is chiral here. So both of these systems actually have the same conformal weights, which is here for the B's 2, 0, and for the C's, we find the compensating -1, 0. In particular, with this, for example, you could plug it into what I gave you on the last slide and calculate things like central charge, and you would find the usual -26. Now, as usual in the BRST, we now want to introduce a BRST operator Q. And our Q is defined to act on our fields, say, X as C tilde P mu plus C dx mu. Let me say, I will, the transformations under T are standard and you can read them off from the symmetry transformations. So I will not spend a great amount of detail on these. So for P, we just find the C P mu, and Q finally acting, for example, on E tilde, we find D bar C tilde plus E D C minus. Okay, the important part is how Q is defined to act on our newly introduced B and B tilde ghosts. And they, sorry, this is a slightly unfortunate notation. These are the two constraints that we gauge, but I want to introduce new fields T and H, which are the standard Nakanishi-Lautrup fields that you usually introduce in your BRST quantization. So also as usual, we'll then add a gauge fixing term to our action, which I'll call GF. And what this is just standard. It's just the action of the BRST operator on B times whatever gauge fixing functional we choose in, well, in this case, E, and the same for B tilde, and this can be a different one, F of E tilde. Now, usually we would like to, meaning in the absence of vertex operators, a good choice is to choose this F tilde of E tilde to be just E tilde, meaning we're actually setting our Lagrange multiplier E tilde to 0. And then you can just integrate out everything. And what you end up with is the following gauge fixed action, which is 1 over 2 pi P dot D bar X. And then from our gauge fixing term, if you go through this, we just pick up B D bar C plus B tilde D bar C tilde. Now this is wonderful. We now have a free linear CFT that is wonderfully easy to calculate with. And in particular, all the OPEs from our last slide hold. So for example, let me just give you X mu of Z, P mu of W just becomes delta mu nu over Z minus W. And C and CB and C tilde B tilde you can read off directly from the last slide. Now, you could also calculate what now the whole central charge anomaly for this is, which is just the requirement that Q square equals 0, and I invite you to do it. But what you find is that this actually is anomaly free in 26 dimensions. The calculation looks really similar to the bosonic string, and it's remarkable that you get the same result out. You just end up with 26 exactly like in the bosonic string. But before we jump to any conclusions here, remember we there's more things we wanted to add. We just talked about the bare action right now, and we know that in principle, we will have to add different meta actions here to describe different theories. So for example, we have no reason to believe that just the bare action that we were just writing could give us, say, gravity. In fact, we have good reason to not believe it's not true, because nothing in what we've been writing can give a Pfaffian. So that's a good reason to look a bit in more detail at what actually is the spectrum of what we're writing and what the worldsheet meta action is that we should include. Now, so the first thing to do here is to look at the structure of the vertex operators, just with the action as it stands right now. So what we want to look at are our four physical states, and we know they have to be in the BRST cohomology. So let me just remind you, we've used, as usual, the standard sort of radial quantization and state operator correspondence, so that all of our states are encoded in local operators V, and being in the BRST cohomology just means that Q acting on V has to be 0, but we don't want V to be Q on something else. Now, the natural ansatz that we can make for BRST closure, we make the following ansatz. We want to construct our vertex operator, say, if you're familiar with the string, as follows. We want to include a factor of C tilde. And then now the rest is where this becomes interesting. This just means we're looking at a vertex operator of ghost number 2. And the first part I won't specify, but the second part is that we want to look at momentum eigenstates. Now that's certainly something that is going to be sensible. And this W here that I haven't specified yet will depend on what worldsheet meta we're including. If we're including nothing, then the only thing right now that we know is that W can only depend on P and X and dP and things that we can construct out of P and X. Okay, now two things to note here. Two things to note here. The first thing is, let's first try to find out something about this W. So to find out, to be able to say anything about W, we should first think a little bit about what our plane wave factor actually looks like and what its properties are. And there's one thing we can immediately see, which is if you look at what comes out of the stress energy tensor acting on our plane wave factor, we find that this only comes with a derivative term. Which means we can immediately conclude that the conformal weight of our exponential factor is just 0, which is, if you want, what you expected from, since we know that X also is just a map. Now, from this, on the other hand, we can conclude that to be BRST, in the BRST cohomology, we have to pick W such that it has weight 2, 0 for Q acting on V is 0. So it's a good idea to go through these calculations yourself and check that, yeah, you're happy with what I'm saying. Now, we can repeat the same calculation with the other constraint, P square. And what you find is that you pick up a term K square plus more terms. So this means that in the BRST quantization for QV to be 0 is completely equivalent with having k square equals 0, meaning our spectrum manifestly only contains massless states. Now, that's something that's very nice because that matches up well with our intuition. We said our target space is the space of non-geodesics, so the space when that naturally describes how massless particles propagate. But it is very nice to see this coming out explicitly in our BRST quantization. Now, at this point, we could really go ahead and write down an ansatz for omega, and something that's natural to write is we could split this as an omega L or WR, where these two are meant to remind you of the half integrands of building blocks that we had before, and each of these have weight 1, 0. And then, just given what we have, there's a natural ansatz that you could make, which is just to put this as epsilon.p. And you can certainly do this and also go ahead with a calculation, and you will find an amplitude. But it turns out to be none of the amplitudes that we discussed. It will be an amplitude in the CHY representation in the general form that we gave, but it won't be anything that we saw on the first few slides in lecture 1. It turns actually out that this describes an unphysical gravitational theory. It's a higher order gravity theory. And if you're interested, I have a reference that I'll give you if you want to read up on that. But this really means that for any interesting theory, we'll actually have to add worldsheet matter. By interesting, I mean for a physically interesting theory. And very much mimicking what we discussed when we were discussing the CHY amplitudes, there's going to be two building blocks, our main choices that we can use to construct this WL and WR. So our first choice is going to be a current algebra as J. And here we'll take J just to be any current. The only thing I'm going to specify is that it transforms in K sigma, and will allow any Lie algebra G here. In particular, this means that, sorry, JB of W will have an OPE that looks like, let me write this as kappa just to avoid confusion with anything else, over Z minus W square. But this is here really just the level, and delta is your killing form. And the term that's usually important for us is the FABC JC W over Z minus W, meaning here you find the structure coefficients of the Lie algebra. Now, how do we use this? In vertex operators, it means that we want to construct our W, L, and R as TA, JA. Well, if this is at a point Z, then this one's at Z. Okay, so this is option 1. Option 2 is we can construct a version of well, let me just call this a fermion matter action. Which will take to be the following. I should say that for the current algebra as J, I didn't specify what implementation you want to use for this. You could choose a free fermion realization of this, but anything you want to choose is fine for this one. Just giving different realizations of the Lie algebra here. That's why I didn't spell out the precise action there. Here, this will be important for us, though. So for the fermions that we can possibly include, we will want to take the action psi mu d bar psi mu, where mu is again a space-time index. So this one runs from 1 up to 1 from 0 up to d minus 1 if you want. This is the free part, but we also want to gauge, well, first of all, we want to gauge an additional current psi dot p, and then to keep there's a worldsheet theory, we should also gauge the stress energy tensor, which I've included back here, the chiral stress energy tensor. Now, to make this is a CFT with the following assignment. H psi has to be 1/2 0. H chi has to be -1/2 1. And that's it. That's everything new I introduced here. Now, note that this is non-trivial. And in particular, we have a term here, which is this psi dot p term that couples to our bare bosonic action that we were writing before. And in particular, this generates new symmetries for us. So we find that this has new, and it happens to be symmetry, which is generated by p dot psi. And I've spelled it out for you here. It's helpful to check this once in the action so that you can see this. But what is remarkable about this, if you're familiar with the string, this is something that will look very intuitive to you. But in contrast to this string, note that this gives us a worldsheet gauge superalgebra, meaning we're not ending up with worldsheet super diffeomorphisms like in the superstring, but it's just a worldsheet gauge supergroup in the end. Now, what does this look like? Well, just look at what p dot psi, let's say p dot psi on W, what the OPE gives to you. And you'll find that this becomes p square of W over Z minus W. So in particular, the two don't square to T, but instead we find that the stress energy tensor, but instead we find the P square constraint here. Okay, let me tell you what we should include in the vertex operators to wrap this up. So for the vertex operators, we want to include here WL, R is briefly before that, let me just mention, so since we found a new symmetry, when we BRST quantize, we will also have to introduce the corresponding ghost systems, and I will call that ghost system beta gamma. This is now a bosonic ghost system, and we have H beta is 3/2 0, and H gamma is -1/2 0, with the usual action coming out of the standard gauge fixing. Okay, in that case, we're now ready to look at how this could contribute in vertex operators, and we'll see that any of these half vertex operators can take the form delta gamma epsilon dot psi. Do go away and check that these have all the correct conformal weight, what I'm writing down here. Should also say that as in the RNS string, superstring, this will have a Riemann sector, but we won't be touching on this today. Okay, so I've given you now a couple of ingredients. Let me try to summarize this as what models this actually results in, because in total, we end up with 3 models. Now, the first one is just a model that I'm going to call by a joint scalar, where I'm choosing the meta action just to be Sj, possibly plus some other current algebra Sj tilde, although you can, of course, choose them to be the same. Then there's also the super Young-Mills one, where we just choose this to be Sj plus S psi. And finally, for supergravity, we're going to choose this to be S psi plus S psi tilde. And I will often use the words heterotic model for this and for this RNS ambitwistor string. Now, some comments. You can calculate the central charge anomaly in all of these. And what you'll find here is the standard to d minus 26 that gave us d equals 26 when we didn't include anything, obviously plus whatever current algebra central charges you included. In the heterotic model, you can check how the psi system modifies this, and it turns out to give this. Whereas in the RNS model, which is going to be the one we will focus on most, we just find the same as counting as in the standard RNS superstring. And I would strongly encourage you to take this away. It's just a 1-line calculation, and check that you end up with the same results. Now, one more comment before we move on to this is that what is the spectrum of these theories? I've told you what type of vertex operators appear in all of these models, but any model that doesn't have both the psi and the psi tilde will also have the type of vertex operators that we wrote down before we actually started our whole discussion of what action to include. Meaning the bi-adjoint scalar theory and the super Young-Mills theory should come with an asterisk, because then to warn us that in their spectrum, we are going to find unphysical gravitational states. At tree level, this won't bother us. For today, you can absolutely put this on a hold. But tomorrow, this means that the one that we'll come back to for loop calculations is supergravity, because we don't want to worry about for our first calculation about whether we can project these states out of the loop or not. Okay. So in my last bit, we will now actually do the main thing that we set out to do with this theory and calculate amplitudes in it. Remember, so what we're hoping to find is that this matches the CHY amplitudes. So we have 3 models that we can go ahead with and calculate. Now, schematically, just to remind you, and let me be brief with this, is that we use conformal transformations to map some complicated worldsheet that I've tried to draw up here to just the sphere with marked points inserted, which are our vertex operators, which encode states at infinity. Remember, so this relies on the fact that we have a map from the cylinder to the sphere, which identifies the origin with the infinite past. And so we do this locally on each of these legs and glue it back in. And that is what gives us this prescription with these small points, marked points, just small points removed. Let me also remind you, so you've seen this in, say, Ollie's lectures already, at least partially, I think, that what governs this is that our action, as we were writing it before, was fine as it is, but we're free to include a Gauss-Bonnet topological term, and then that tells us that there's really a coupling constant sitting out front that comes with different powers at each order in perturbation theory. Okay, at tree level, so this is what we're going to do today. This is what we're going to do tomorrow. Or next lecture. At tree level, let me remind you from the string that something that you should be familiar with is that there is a residual conformal symmetry on the sphere, which just corresponds to the Möbius transformations. This is all something that we're already taking into account. This just corresponds to our counting before, that the sea ghosts developed 3 zero modes on the sphere. Okay, so let's dive straight into this. The first thing that we have to revisit, you might have heard this, I was careful about how to phrase this, is that we have to revisit the Brst quantization in the presence of vertex operators. Why? Now, if we're careful, you might have already seen that on a generic sigma n with n punctures, we cannot choose f tilde of e tilde is what I called our gauge fixing functional to be e tilde. Why is that? Well, if you look at the gauge transformations, then you will see that we're only free to vary e tilde within its cohomology class. So in particular, we found that all transformations for e tilde after setting e to 0, which we will want to do because otherwise our quantization will be hard, is just d bar alpha. So we're only varying it within a cohomology class. And so we conclude that E just varies within not 1 of sigma T sigma with marked points. So we're just not free. We don't have enough gauge freedom to choose this. The best we can do is to pick f tilde of e tilde just to be, well, e tilde, which we wanted to do, and then a new term, which is minus, well, we know what this has to be. It just has to be whatever basis we have for our cohomology group. It's a finite dimensional group, and some coefficients here. So this R, you can count the dimension of the cohomology group. This runs from n minus 3, and at higher genus, there would be a plus 3g here. Now, let me just spell this out. Mu R is a basis for our cohomology group, and these SR are just some bosonic parameters. Under BRST, we thus have to specify, well, Q acting on SR will just give us some other parameters that, let me remind you, because SR is bosonic, these QR will be some fermionic parameters. And then second, this is point 1, and second, it instructs us we should integrate over DSR, DQR. Now, with this in mind, let's look at, with this gauge fixing functional that we've chosen, let's look at what terms we actually find in the action. So in the action, what we now find is that S, including the gauge fixing functional, contains 1 over 2 pi standard term. So we want to look at every term that contains E tilde, since that is the field we're currently concerned with in our gauge fixing term. So we had the minus e tilde p square, that is the part that comes from our standard bare ambitwister action. And then remember, we have a term that comes from the gauge fixing, which is just Q acting on B tilde F tilde. And that produces us the following. So we have E tilde H, where H, remember, is the Nakanishi-Lautrup field that we introduced. Then we have the sum over R. And here we find two terms. Again, the H plus SR, sorry, QR, mu R, B tilde. And that's it. And this part, I've told you this already, comes from Q acting on B tilde F tilde of E tilde, with the choice of for F tilde that I've made on the last slide. Now, if we integrate out DSR and DQR, what we find is that in the correlator, we end up with the following insertions. Well, okay. First, integrate out H, that sets E tilde to be SR mu R, and then integrate out SR. And then what we find is that this is the only place SR appears is in the action here. And what we're left with is just some delta functions from integrating out SR, with here mu R p square. And then from QR, because these are bosonic, this won't get delta functions, but we'll find the same type of integrals over mu R, but now with B tilde. I will occasionally, when I'm to keep things compact, I will write this with these brackets. If you're familiar with this, it's called the Serre duality pairing. But if you're unfamiliar with this, don't worry. This is really just a notation for what I've written here. Now, if you look at this for a second, you can see that there is something suggestive, namely that there's delta functions here that run from r equals 1 to n minus 3. That's wonderful. That's something that we're actually quite keen on. And so what we can do is we can choose a good basis where mu I just extracts the residue at a marked point, sigma I. That's one choice of basis. There's other choices, but at tree level, this is a really good one. And then we can absorb this into our vertex operators. And we find some new vertex operators that I'll try to write with these curly V's, which then just become delta bar residue at point I of P square, VI, where VI was our vertex operator from before. Now, I'll be very brief on this, but the main idea for the fermionic constraints, P dot psi, is that you just repeat a version of what I've been telling you. Now, once you go through this, this is equivalent to just doing descent on the vertex operators. And in particular, what we'll find is that when you go through this, these insertions in the correlator that we found here, instead of these, once you go through the same thing for the fermionic case, we find insertions, and in this case they have a name, of so-called picture changing operators. I don't know if Ollie touched on this in his course, but If yes, great. If no, I'll tell you all about them that you will need to know for these calculations. And these PCOs take the following form. They're epsilon of z, and they have delta of beta, where beta, remember, is the ghost that I introduced for the p dot psi constraint, and then the p dot psi of z. Now, as before, you can absorb them into the vertex operators, and I will denote this just by a superscript 0. Well, in this case, it is better to denote this by 0, 0, because there's 2 for the RNS model. This is going to be in the RNS case. Otherwise, just 1, which I will define as the limit as this, as W goes to Z of this PCO operator at W and the vertex operator at Z. Now you can check what this gives, and it has a particularly nice form for both the RNS and the Young-Mills and the heterotic model case. And what we find is that this just takes the following form: epsilon dot psi plus, let me get the sign straight, k dot psi, epsilon dot psi, and then the same epsilon dot p plus k dot psi tilde, epsilon tilde psi tilde, times the usual plane wave factor e to the I k dot x. Okay, there's some details that I skipped here, but they should be relatively easy for you to fill in. So now, finally, we can go ahead and now actually look at the correlator. Now we do know what the form of this should be, because we've now been careful about the Brst quantization in the presence of vertex operators. And so I could write this with the picture changing operators and everything still at arbitrary points, but in the simplest possible incarnation, this is just C1, C tilde 1, V1, C2, C tilde 2, V2. These are our vertex operators that we included. And then I'll just checking a 0 mode counting guarantees that from here on we need them in this 0, 0 picture. And then we need to include the remaining from 4 to n in the integrated picture. Remember, that involves all the delta functions. So here we'll have a vi of 0, 0, which, just let me remind you, involves the delta bar residue at I p square and has the vi of 0, 0. Okay, so in the next 10 minutes, this is what we actually want to calculate, but we've done all the hard work. By now, this is really mostly putting things together with one nice trick that we'll see. So first, the easy bits. So for the BC system, we can just go ahead and calculate this, and we'll see that we'll get the volume of SL2C factor out just by a standard calculation. You can go ahead. This is something you can also just directly see here. From the B tilde C tilde system, we'll get a similar Jacobian factor. And this is precisely the Jacobian we needed for the prime here in the scattering amplitudes, in the scattering equations. Now, finally, last easy comment, something that in the px system, we can look at the x0 modes. And you can see that there's no dependence anywhere, so we can integrate this out straightforwardly. And what we end up with is, well, d, but this is the critical, in the critical dimension, with just momentum conservation. Okay, so to go beyond this, we would now next like to, well, two things. We have to do the px correlator, and we have to do the correlator of the various worksheet meta systems. Now, let's look at the px correlator first. And for that one, there's a really neat trick that you can use, which is the following. Notice that in the vertex operators, they all have roughly the same form. They all take the shape of some function of p, and then e to the ik dot x. And this doesn't depend on the picture. The same is true for the ones in the 0, 0 picture. So what we can do, our trick is to take, these exponential factors, e to the ik dot x, into some effective action, meaning the relevant terms will look like the thing. So we'll have the p dot d bar x in our action. Remember, we gauge fixed everything to 0 and integrated out everything else we couldn't set to 0. So there's no more p dependence in our action here. And we paid the price by having the delta functions in the correlator that depend on p squared. And from these, we now get a plus 2 pi I sum from j equals 1 to n kj dot x, but they only were supported here. Sorry, if this is at a point sigma, this is also at sigma. So this is sigma I. So we really also need a function sigma minus sigma I here, just to match form degrees. I think I need a d sigma here as well. Okay, but once we have this, now let's look at our correlator. And with these taken into the action, nothing depends on x anymore. So we can actually integrate out first x explicitly, and then p. And what we find is that p then, just after integrating it, localizes onto its classical equations of motion. And I suggest you follow through these two steps, but you then find that d bar p mu has to be 2 pi I, precisely the sources that I have here. Ki mu d bar sigma minus sigma I d sigma. And at this point, you should already see the hints that we're home, that we're gonna recover the CHY formulas at this point. Why? We can now solve this. Remember, everything we're saying right now is on the sphere, so we can solve this very much straightforwardly. And we find p mu is the sum from I equals 1 to n ki mu over sigma minus sigma I d sigma. And this should really look familiar to you. This is now exactly what we were constructing in the beginning for, well, at the end of the last lecture, for the scattering equations. And in particular, if we just plug this into our constraints that are sitting in the delta function, we now really find the residue of I p squared becomes what we were writing before in the very beginning for the scattering equations, ki dot kj over sigma ij. So these are really the scattering equations, EI. Excellent. So what we've concluded now is that if we calculate the correlator AN, we find precisely, well, this one was no surprise, the moduli space integral, but we find precisely the CHY measure here that I'm just going to abbreviate. And then what we haven't calculated yet is that we have still the correlator left to do of these contributions omega 1 up to omega NL and the right contributions as well, all supported on P is Kj b sigma over sigma minus sigma. And now, so the only thing we have left to do is calculate these two. And at this point, I will tell you that these are standard calculations that you can go ahead and do. They're really not hard, especially the first one. So the first one will find that Cn is just T A1 J A1 sigma 1 up to T AN AN of sigma n for the single trace here. Single traced contributions, or if you have a level 0 system, this is no problem anyway. And for our other choice, for the fermions, we find that, well, what does this look like? Let me just spell it out for you. So we have the two fixed vertex operators in psi of sigma 2. And then we have all the other ones in what I was calling the 0, 0 picture with epsilon I dot p plus ki dot psi, epsilon I dot psi. All of this is at sigma I. Close the correlator here. Now you can calculate this, and what you will find is that you find a -1 over sigma 1, 2 times the Pfaffian of a big matrix M that looks like the M that I gave you in the beginning, but with rows and columns for particles 1 and 2 in the A block removed. Now, just if you look at the definition that I gave you there, that is precisely the Pfaffian prime of M. Now, I would encourage you to go through this. You can probably see sort of roughly where everything comes from. The epsilon dot epsilon entries will come from contractions among the psi's. The epsilon dot k entries will also come from here. K dot k also between different vertex operators here. And the epsilon dot p's will fill in the diagonals on the matrix M. Okay, so what we concluded with here, let me maybe highlight this, is that our correlator, let me just sketch this schematically, C1, C tilde 1, V1, and everything else up to the I equals 4 to n, indeed reproduces the CHY amplitudes, at least for the external states that we were interested in, meaning for Biot and scalar, for Young-Mills, and for gravity. So it really does what we constructed it to do. Now, one last comment is maybe due. So the scattering equations, formalism, and the CHY formula, so the part on the right hand here, that one lives in any dimension D. Whereas, as I pointed out, really on the left-hand side here in the correlator, we want to work in the critical dimension. So what's going on here? Now, the reason for this is actually quite simple. You're free at tree level to just restrict your momenta to lie in lower dimensions. There's nothing nothing non-trivial that happens. And so you know that the amplitudes will agree. The first time this comes to haunt you is at loop level, and there will have to be much more careful with this. So with that said, I'll wrap up here our tour de force through ambitwistor strings at tree level and the CHY formulas. And what we'll do in lecture 3 tomorrow is we'll see how to push this on at one loop. Now, our one loop discussion on the torus is going to be by time necessity, a little bit schematic, but we'll see what the key features are and meet the key ingredients. And then we'll discuss what the amplitudes are that we find, or the integrands. We'll have to be much more careful about what dimension we're in and what theory we're working with. And then we'll see where the nodal sphere comes in all of this, because so far we've run 2 full lectures and the only thing you've seen are spheres. The nodes haven't come in anywhere. But all of that for lecture 3 tomorrow. Thank you.